Let's talk about double integrals, but for general regions. So before, we were dealing with double integrals, but we were dealing with rectangular regions. So the bounds were pretty easy to do, right? You have double integral of some multivariable function, f of x comma y, dx dy. And you see how the x bounds are from 3 to 6, and the y bounds are from 2 to 4. So it's pretty easy to do the bounds. But what happens if one of your bounds is actually a function? What happens if the region that you're looking at is weird? It's not rectangular. Usually what double integrals are associated with, or in a lot of scenarios, you might see them associated with volume. If we look at this three-dimensionally, let's say this is the x-axis and the y-axis is the z-axis. You're going from 2 to 4 in the x direction and 3 to 6 in the y direction. And you're trying to find the volume of this surface, essentially trying to find the volume of this surface in those bounds, right? So it's going to be like this rectangular block I've drawn here. It's not really a rectangular block, but kind of simplified it to look like that. The reason why you're finding volume is because dx dy, think about what that is, right? You're moving a tiny step along the x direction, a tiny step along the y direction. You're essentially forming a tiny rectangle. And when you multiply dx by dy together, you get a tiny area, which is also why dx times dy is called dA. And when you multiply that area by a height, well, then you get the volume of a tiny rectangular prism, right? So when you multiply by the height, area times height gives you volume, right? Because this is essentially length times width, and you're multiplying it by height, so length with height, volume. Another interpretation you might have heard of is, let's say that dA, let's say that represents some kind of area density. And instead of f of x comma y representing the height of a specific function, let's say that represents a density function. So at every point on here, every point on the surface here, represents the height of that function represents a specific density at that location. And so if you multiply density by the area density, you get the mass. So the double integral, when you evaluate it out, it gives the total mass of whatever surface that you're looking at. So if the density of that specific thing is meters squared, so if you're looking at a specific density, right, which is that height, and you multiply it by that area density, which you can think about as grams per meter squared, well then the meter squareds cancel out and you just get grams, which is the mass. Now I'm going to remove the height here, so we're only going to be focusing on area, this dA part, and we're not going to be focusing on volume just yet, all right, because we want to build from the basics. So what's the difference between this and this? Right, you know that both of these, if you were to write out the bounds here, right, both of these would represent the area of some specific region. In this case, right, it would be this rectangular region, right? So if you were to write it out here, the x value would go from 3 to 6, 2 to 4, and for this one, it would go from 2 to 4, and then 3 to 6. Well, what does this inner integral represent? The integral from 3 to 6 of dx. Well, this integral right over here is from 3 to 6 of dx, and then when you just evaluate this out, right, this is just going to become x, and then you evaluate it from 6 to 3. So this is going to give you a value of 3. And so that means that this is going to give you this distance right over here, right, this one-dimensional length. And then you're basically saying, okay, you've done it for this y value, well then do it again for the next y value. Find the length of the next section. Do it again for the next y value, right? Move another dy up. Do it for this section, this section, this section, and so on. And when you do it from 2 to 4, right, you do this integral infinitely many times from 2 to 4, capturing all this area, well then, this is going to give you the area of this rectangular region. And so notice how when this dx is first, what we're doing is we're sweeping across in the x direction, right? We are sweeping across in the x direction. So this inner thing right over here represents sweeping across. While this dy here a lot of times it's actually pretty easy to think about dy as like something that's like pick a constant from here. So this dy here, a lot of times what people do is they pick a constant y value and they say, okay, if the dy is constant, then what this inner integral is doing is we're just sweeping across at that specific y value. And then we just keep doing it from these y bounds. Now, when you look at this integral here, we can apply the same logic, right? We're going to choose a constant x value. So let's say we're looking at this x value here, and then we're going to sweep across in the y direction. So we're going to sweep across in the y direction. All right. And so doing that across this entire x bound, right, sweeping across in the y direction across this entire x bound, summing this all up eventually gives us our entire area. So yes, you can think about dx, dy as like that dA, like as like an area type of thing, right, where you're just multiplying them together. But another way to think about them is you're keeping one variable constant at some point, you sweep across, and you move another, in this case, another dx across. Now let's move away from rectangular regions and let's get into general regions. So you got all these funky shapes here, but what's kind of interesting is that type 1 regions, as they call it, type 1 regions are when the outer integral is with respect to x. So you notice how in the diagram, the x is on the outside, meaning that this is kind of the thing that we're looking at it from a constant perspective, and then we're varying this inside integral here. So what we're doing is we're looking at a constant x value, and then we can find out the height, or in this case, the height of this function, right, by doing this inner integral here with respect to y, right? So you have a constant x value, and you look at it from the y value, right? Constant x value, shoot it up, and then you find the y value here, and then you just sum it all up, right? And the reason why type 1 regions are special is because, well, it would be very hard to reverse this. So for type 1 regions, if instead of dy dx, right, instead of dy dx, if you did it the opposite way, so you did it from dx dy, ignoring the bounds here, right? If this was dx dy, what this is saying is that you look at a constant y value, and then you sweep across in the x direction. And this seems good at first, right? This looks fine at first, but all of a sudden, when I'm up here, I can't sweep across the entire thing because there's something blocking me. And so type 1 regions, what you usually want to do is you just want to integrate first with respect to y, and then with respect to x. And another thing that's special about type 1 regions is that, well, instead of the bounds being constant, well, the bounds are actually going to be, they can be represented as functions. And so for this inner integral right over here, the y value can range from a function like f of x to y being equal to a function, let's just say g of x. So you can see that, right, for a constant x value, well, you're going to sweep across it, and you're going to end it at this top function here. So you can say that this top function here is g of x, right? This is the top bound, and then the bottom function here, whatever this is f of x, right? So every time that you sweep across, you see that we always start at f of x, and we always end at g of x. That's why this is my lower bound, this is my upper bound. Now, for type 2 regions, it's just going to be the opposite of that. For type 2 regions, first what we're going to do is we're going to integrate with respect to x first, and then with respect to y. And then your y value is going to be a constant. So y is going to range from c to d, in this case, c to d. And the x value bounds can be functions. So the x value bounds can be from f of y to g of y. So in this case here, remember what this double integral is saying, right? Let's say that we're looking at a constant y value. We look at a constant y value. We're going to sweep across that in the x direction, right? So in this case, we're going to sweep across this in the x direction. And it's going to start from, and you notice how when we sweep across, it's going to start from f of y, this function, let's just say this is f of y, and we're going to always end at this function here. Let's just say this is g of y. And you're essentially going to be sweeping across from c to d, which is why this dy here is on the outside. If I try to do this with respect to y first, and then with respect to x, then we run into the same problems as we did before. We see that what this is doing is we're looking at a constant x value here, and we're trying to sweep across it in the y direction. And this works for this region here, but then when we get to the end of this bound, then we can't sweep across all the way. And so that's the problem here. Type 1 regions, your x bounds are constants, and your y bounds can be variable. They can be represented as functions. Type 2 regions is a swap. Your y value in this case are bounds, right? Your y bounds are constants, and the x values can be functions. So now let's move on to some practice problems. Let's say that we want to find out the area enclosed by these two graphs right over here. So the first graph, x is equal to y squared, is going to be like a sideways parabola, and the second graph is going to be x is equal to 4. So this is x is equal to y squared, and this is x is equal to 4. So we're essentially looking at this region right over here. Now, which integral do we use? We know that we're going to have a double integral, but are we going to do this with respect to x first and then y, or y first and with respect to x? Well, let's take a look. Let's say that we look at a specific y value, right? So we look at a specific y value and we trace across. You always see that our lower bound is our parabola, x is equal to y squared, and the upper bound is x is equal to 4, right? It's consistent all the way through, right? So that means that if the y value is kept constant, but you keep on integrating with respect to the x value, well then this is the way, right? Constant y value, look at that dy as sort of a constant for reference, and then dx right over here is the thing that you're varying. If you looked at it the opposite way, so this would be dy dx here, well this is saying that, let's say we pick out a specific x value, let's say this x value here, and we want to sweep across in the y direction, but then the problem becomes the x is equal to y squared is the bottom and the top bound. That doesn't make any sense, right? So we're going to go with this one. All right. Now the question is, what are the x bounds and what are the y bounds? Well, the y bounds are pretty simple to find, right? You just have to find these two intersection points, and you find their corresponding y values. So in other words, we want to find out, you have x is equal to 4, you have x is equal to y squared. You want to find when they're equal to each other. So you have to set those equations equal to each other. So 4 is equal to y squared. Right? Set them equal to each other, just substituting 4 into x, and you get that y is equal to plus or minus 2. So at y is equal to 2 and y is equal to negative 2, remember, the thing on the outside, the integral on the outside, always have constant bounds. It's the integral on the inside that has the variable bounds. So what are the variable bounds for this function? Well, with respect to x, right, we know that our x value always starts from the parabola and it always ends at x is equal to 4. So we're going to start at x being equal to y squared, and we're going to end at x is equal to 4. So these are our bounds, right? So in summary, our x bounds go from y squared all the way up to x is equal to 4, and our y bounds go from negative 2 to positive 2. And now all we have to do is evaluate the integral to get the area. So this is like a 1 dx, I guess you could say. So this is going to be the inner integral, so the integral of just 1 dx from y squared to 4. That's going to be equal to x ranging from y squared to 4. Evaluate it at these two, and you get 4 minus y squared. And now you're now at the outer integral now. So this is an integral from negative 2 to 2 with respect to y. So now we can do, this is 4y minus y to the third power over 3, evaluated at negative 2 2. Plug in 2 here, you get 8. This is 8 minus 8 over 3. And then you subtract that from, so this is negative 8 minus, that's going to be negative 8 as well. Negative negative makes it positive, so this is 8 over 3. And this becomes a negative, this becomes a positive, right? Because you distribute the negative sign in there. So you get 16 minus 16 over 3. All right, and then 16 is just 48 over 3 minus 16 over 3. That's going to be equal to 32 over 3. That is the answer. All right, find the area bounded between these two curves right over here. So what do we have? Our original thing, x is equal to 0, which is just the y-axis. And then x is equal to 9 minus y squared. That's just a parabola like this, where it intersects 9, 0, right? Because this is like a positive 9. So you have the negative y squared, which it turns from a parabola facing this way, and it swaps it to a parabola facing this way. And then you're moving up in the x direction by 9 units. So you're essentially finding the area of this region here. So the first question you always want to ask yourself is, which comes first, dx or dy? Dx or dy? Well, it looks like if we start at a constant y value, so we look at a constant y value, and then we look in the x direction, right? So we pick a y value, go in the x direction, constant y value, go in the x direction. You see that we always start at x being equal to 0 to x being equal to 9 minus y squared. And our y values are going to range from, well, we have to solve them, right? So the y values, in order to solve them, we just set them equal to each other. So we have 0 is equal to 9 minus y squared. And then when we solve for y, we get that y is equal to plus or minus 3. So our y ranges from minus 3 to 3. Right? So what we're saying is from the y value minus 3 to the y value of 3, well, we're essentially going to sweep across in the x direction from x is equal to 0 to x is equal to 9 minus y squared. And that's how we get this area here. If we did it the opposite way, then this parabola would be both the top bound and the lower bound. That wouldn't be good. Now let's solve it. So this is just the integral of 1. This is going to be 9 minus y squared. dy, integral from negative 3 to 3. And then this is going to be 9y minus y to the third over 3 evaluated at negative 3 to 3. And then so 27 minus 9, which is just 18. And then that's going to be minus, and now we evaluate it at negative 3. So that's going to be negative 27 minus, that's negative 27 as well. That turns into a positive 27 over 3 because 2 negatives cancel out. That's going to be 9. This is negative 18. So negative 18 minus 18 is going to be 36. That is going to be the area of that region. Let's take a look at this one. So first, visualize it. You want to see what region you're enclosing. So let's see. We can factor out this. So this is x times, and then this would be x squared minus 4. So this is just the difference of squares. X minus 2, x plus 2. A 0 here, you have a 0 here, and then you have a 0 here. And the cubic function is going to look something like this. And this is enclosed by y is equal to 0, so it's going to be enclosed like this. So we're essentially trying to find out the area here and the area here, right? So how can we do this? Remember, after we do this step of graphing out, finding out which regions that we want to take care of, we want to determine if dx, if this is dx dy, or if this is a dy dx. All right. So let's take a look at region 1 first. So for region 1, this is going to be double integral. And how do we do this? Well, it looks like my lower bound is always y is equal to 0, and my upper bound is always y is equal to x to the third power minus 4x, meaning that we're going to keep a constant x value, right? X value, let's say that's a constant value. Well, the y value always has y is equal to 0 on the bottom, and then y is equal to x squared minus 4x on the top. Therefore, this is going to be integral where dx is on the outside, because you're looking at a constant x perspective. The two y bounds are from y is equal to 0 to y being x to the third power minus 4x. And then the x bounds, well, it goes from negative 2 to 0. Okay. Now what about region 2? So what about this region right over here? Well, we can kind of do the same thing, right? Except this time, this is beneath us, right? So what's going to happen is our lower bound is now our lower bound is going to be y is equal to x to the third power minus 4x. Right, that's our lower bound, and our upper bound is y is equal to 0, right? And then this is going to be from 0 to 2. And then so if I sum up the value from R1 and R2 together, then I should get the answer to this. Let's start out with R1. So this is going to be x to the third minus 4x dx, integral from negative 2 to 0. This is going to give you, let's see, this is going to be x to 4 over 4 minus 2x squared evaluated at negative 2 and 0. So you plug in 0 into all these, you just get 0. And you plug in negative 2 into all of these. And so that's going to give you 16. That's 4 minus, that's 2 times 4. That's negative 4. That's going to be equal to 4. For R2, you're going to get, this is the integral. I'm going to evaluate out the inner integral. So the inner integral is just going to be, you just get x here, so you plug in, or sorry, y here, so you just plug in 0 into y, that's 0, minus, and then you plug in this into here, and you get x to the third minus 4x dx. And now this is just going to become negative x to the third plus 4x, and then the integral of that from 0 to 2 dx is going to be negative x to 4. Oh, almost forgot to put a 2 here. Sorry about that. All right, so now this is going to be negative 4 plus, and then 2 squared is 4 times 8, and then minus, and that's just going to be 0. So this is going to give you an area of 4. And so 4 plus 4 here is going to give you an area of 8. So when you add up the area of 4 here and 4 here, you get a total area of 8. Now, why does this make sense? Well, think about it, right? Let's say that you were doing single variable calculus, right? Well, you notice how this is like an odd function, right? X to the third power minus 4x is an odd function. And in single variable calculus, the area beneath this, right over here, the area beneath the x-axis would be counted as negative. So the integral from negative 2 to 2 of x to the third power minus 4x, well, if you think about it, because this is an odd function, this area would cancel with this area, leading to an integral value of 0. But because this is multivariable calculus and we're just trying to find out the area of each of these regions, well, then the answers would be positive. So this would be, instead of negative 4, we don't care if this is beneath the curve. We're just trying to find out the total area. So this is going to be a non-negative answer. It's going to be a positive answer because we have area, right? So that's how you can interpret it in the context of single variable calculus.